All right. Any volunteers to offer a prayer? But if you didn't volunteer, I'll make Michelle say it. Keep her from saying. Were you raising your hand? Okay, someone was. Thank you, Cambria. Amen. Thank you very much. Speaking of understanding and not understanding, we're going to start hitting some things. I know a lot of you thought, hey, none of this has been too bad yet. Hardest thing is doing row reduction and not making mistakes. We're going to be hitting some big ideas that aren't going to be as simple. Transformations we're going to hit in a minute. It's not that bad. Coordinates, which we're hitting next time, take a bit to get your head around, at least the technical side of things. Intuitive idea is not that bad. But we're going to get eigenvalues and eigenspaces, and that's really where things get a little new and arguably the most important stuff that you'll be learning about matrices this semester. So if you haven't had to visit any office hours yet, don't be surprised if you feel like you need to visit office hours coming up in the next few weeks. So, okay, quickly, any comments about the forum yesterday? Or yeah, was that yesterday? Didn't it just fill you with joy? Very depressing. It was very depressing. Yeah. It was informational. It was, yeah. Pretty much talked about all the major problems that the world's facing today at the macro level. So, yeah. I didn't quite agree with her her mobility statistic. She said that to argue that mobility is going down in the US, she said that the probability of starting in the bottom, and I can't remember if she said quartile or quintile, but basically at the bottom level, and dying at the top level has gone down 50%. And I can't remember exactly the number of years, but decades. But people are living a lot longer, and 80 and 90-year-olds don't make that much money. But you're basically making a lot of money right before you retire, usually, right? It's in your late 50s, early 60s when you're maximizing your earning potential. And so just because you're dying not in the top, it doesn't mean that mobility has decreased. I don't doubt that it has, but I don't think it's decreased that much. One of the hard things about measuring mobility is, so for the economists, or the economists, I have a whole group of economists that sit over here in my next class, is that it's hard to talk about it in terms of a snapshot because everyone starts low, or 99% of us start low, and then we increase our earning potential and then we go back down. And if you look at whole lifespans, the inequality is not nearly as large as when you just look at a snapshot. Like right now, a lot of you are working what, $12 an hour, but in 4 years you're going to be making 90 grand or whatever it is, depending on your major, 50 grand, 60 grand, whatever it is. Yeah, you're not worried too much about your low income now because you're going to be making more later. Anyway, I'm not trying to argue everything about what she said, but that was just one point that stuck out to me that maybe she was trying to, she didn't have time to go into the details and stuff, but okay. Let's go ahead. I'm going to spend about 10 minutes hopefully on this stuff. So here's the problem of the day. One problem, we're just going to see how well you picked up how to find the column space, a basis for the column space, row space, and null space. And then we're going to dive deeper into like, what does a basis mean? and the relationship between all of these subspaces of a matrix. Okay, so take some time, work on this problem. Did you bring these to bribe me before I graded your exam? No, just kidding. All right. Let's do this. Okay, what's the rank of A? 2. Okay, you start row reducing. You can just add the first row to the second row. Okay, you add the top to the first row to the second row, you get 1, 2, minus 3, 0, 4, 2. This is as far as you need to go to find out what the rank is, because I have 2 pivot positions right there and right there. Okay, so rank is 2. Great. What's the next? Let's finish going down because we need to do it to find out what the. Well, we need to do it to figure out the null space. We actually could talk about what the basis for the row space is now and what the basis for the column space is now. So once I know where the pivot positions are, then I have enough information to talk about the row space and the column space. So the row space are all the rows that have a pivot position. It's the span of all the rows that have a pivot position. So the basis for the row space are these 2 vectors or these 2 vectors. Any vectors in my process, any step in my row reduction, I could stop at and take those vectors, and that can be a basis for the row space. So basis for the row space of A. Well, it's 1, 2, minus 3, and a -1 to 5. Or, oops, I could do 1 to a -3, 0, 4, 2. Or I could go further. Let's go further just for fun. I can get 0, 1.5 there. And then I can use this 1 to get this 2 to be 0. So I multiply this by a -2 and add. So a -2 here will be a -1, and then I add, I end up with a -4. So this is reduced row echelon form. So I could stop there. 1, 0, a -4, and 0, 1.5. So any of these are I could choose as the basis for the row space. Each of these are just linear combinations of these to begin with, and linear combinations are still in the space. So it doesn't matter if you do the originals or you do the n ones or anywhere in between. For row space, it's different for column space, but for row space. Okay. How about for column space? How about that? Well, we row reduce until we find out where our pivot positions are. And then we have to go back to the originals. We have to go back to the originals and pick those as our basis. As we row reduce, it will change our column space. But the row reduction doesn't change our row space because we're just always dealing with linear combinations of the initial rows. But it does change our column space, so we have to go back to the original. So basis for the column space of A, then the set 1 and a -1, 2, 2. Okay. Any questions on finding a basis for the row space, basis for the column space? We'll talk more about what a basis is in terms of a context in a minute. But just a basis is the building blocks for a space. A minimal spanning set. It's enough information that you can describe or get to every point in the subspace, but not so much information that you're dealing with a linearly dependent set. So it's like the ideal. Okay, it's like the Goldilocks. You have enough vectors you can get anywhere, but not so much that you have redundancy. So, okay. So any questions about how to just find a basis for the row space of a matrix and find a basis for the column space of a matrix? Okay. Let's do null space. Then we'll come back to that question about where do different things live. So where does the row space live? Where does the column space live? So let's find the null space. So the null space answers the question, what are all of the vectors or all of the points that give me the 0 vector as a result? So AX equals B, so the null space is all X such that AX equals 0. Okay? So they're all of the, in this case, X, Y's, and Z's, all of those triples, those packets of numbers that would map to 0, 0. So we're really just solving this equation. What values of X, Y, and Z do I need to get 0, 0 over here? So we row reduce. Row reducing a homogeneous system is super, super nice because you don't ever have to worry about over here. It's always just a 0, 0. And we've already row reduced over there. So row reduce, and what do we get? 1, 0, and -4, 0, 0, 1. So 1/2 or -1/2? 1/2, 0. And now What do we notice about this? There's a free variable. There's a free variable. There's infinitely many solutions here. There is always at least one variable, one solution to the homogeneous system. That is, each of the quantities can be zero. Zero this plus zero this plus zero this. So there's always a solution. The question is if there's infinite or not. And if there's infinite, describe what that infinity is. And that infinity in this case is going to be a line. Like any point on this line will give you the solution 0, 0. So, but let's talk about that line. Let's translate this into, I'll use x, y's, and z's. So this is x minus 4z equals 0. And this is y minus plus 1/2 z equals 0. And z equals, I'll call it t. Z is the free variable, right? I can let it be whatever I want. So z equals z or z equals t. So we can translate that back to x, y. The solution now for this system is any x, y, z, where t is going to be 4. Yeah, so you have to, I'm adding the 4 to that side. I'm pulling out the, if I replace my z's with t's and pull them out, I'm going to get a minus 1/2 here, and I'm going to get 1 there. Okay, so this is back to chapter 2, writing down the infinite solutions. So this describes all of the points that would make this solution true. Any scalar multiple of this vector. Okay, and we call this vector is a basis for the null space. Okay. If we end up with a 2-dimensional space, we have 2 free variables, we would have t times a vector plus s times a vector, then those 2 vectors would be the basis. We had to put both of those in there. So, okay. Questions about basis for the null space? Yes? Great question. The question is it possible not to have a null space? You always have a null space. The question is whether it's more than just the 0 vector. So 0, 0, 0 is always in the null space. So if you have, if this was a 3 by 3 and you had 3 independent columns here, or 3 independent rows, then we wouldn't have a free variable. And the only solution to this system would be x equals 0, y equals 0, and z equals 0. So the null space would just be that point. So there's always a null space. The question is whether it's just 0, 0, 0, or it's a line that goes through the origin, or whether it's a plane that goes through the origin, or 3-dimensional hyperplane that goes through the origin. So there is always that 0, 0, 0 that is in there. So, okay, good question. Other questions? Okay, so that's kind of the just computation, how to find these things. Let's go back to number 2. It says if we multiply a vector x by a, we get out a vector b. So ax equals b. Where does x live? So let's use some fingers here. So it could be R1, R2, R3, R4, etc. So for x, what are we talking about? What dimension does x live in? Just raise the number of fingers. Okay, is it R1, R2, R3? If it's R1, don't use your middle finger, please. Okay, so I see lots of 3s, a few 2s. Okay, and how about, where does B live? R1, R2, R3, or R4, etc. And I see lots of peace signs. Nice. Okay. When you do 2, you should do it this way and not this way. Did I already tell you that? So some countries like New Zealand, where I serve my mission, this is the same thing as flipping off somebody. This is not. So this is nice peace sign. Okay, remember the peace sign, not this. So what was that? France is the same. See, so be careful. In Greece, this is bad. So anyone serve their mission in Greece? Okay, all right. Sometimes they'll do the two-handed. Yeah, really bad. Kind of crazy. All right, look at what you learned. Cultural phenomenon in math class. So yeah, so what are we talking about here? So if I think about this AX equals B, and we have a particular A, so I'm going to write out XYZ, and I'm going to end up with this vector, 1, 2, a minus 3, a minus 1, 2, and 5. I need to have a vector that has exactly 3 coordinates here. So this is, we're going to be talking about inputs and outputs today to help us understand what's going on. And so this input here, like you guys have been dealing with inputs and outputs before, like where you think of like f of x equals y, or x is the input and f of x is the output, right? We can think about this the same way. Like usually we don't write it, usually we write it like y equals 2x. You know, we're dealing with something pretty simple here where we think of putting in an x and getting out a y. The structure is the same, except usually we write the output on the right-hand side. But we don't have to. We could write b equals ax. So we're thinking about x as inputs and b as outputs. But what's different for us here is before x was just a real number, you know, x was a real number, y is a real number. But here, x is a packet of numbers, and we get out another packet of numbers. And the input here is some point in R3, and the output is some point in R2. Yes? Yep. Yeah, so it was x is a vector, so it's just one column. Yes. There are other ways to think about it with a matrix times a matrix, but that's more complicated. Stick with the easy one. So this takes a point in R3 and maps it to R2. And that point in R3 might be the number of apples, oranges, and peaches you're buying. And this might be the price in different stores. They're giving peaches away, and you get $3 every peach you buy, I guess. Okay, and then this would be the price at the 2 stores. That's kind of the example that the book does in matrix multiplication. But here, you start off with an amount of each, and you end up with $2 amounts. Okay, so this goes from R3 and maps it to R2. Oh, I'm working in the wrong order here. So here, let's do this. Okay, so we're going to do a really simple example. Consider AX equals B, where A is 1 and 2. So my dollar store down the road for my house, it started to sell some things that are $2. So it's not everything's $1. Some are $2. So the amount I pay just depends on the number of $1 items and the number of $2 items. You could use that as this context. Or you can think of this example, this context I wrote up here. I have 2 foods. One has 1 gram of protein per serving. The other has 2 grams of protein per serving. So pretty simple matrix there. X is the number of servings of each. We'll just call them food X and food Y. So X is the number of servings they get for food X, and Y is the number of servings they get for food Y. And B would be the number of grams of protein that I get from eating those servings. Okay? So, and we'll make the same assumption that we had before, where I'm already eating some of these foods, so I can have negative servings. I can stop eating some. Okay? And so B is actually not the total amount of protein I'm eating, but the change in the amount of protein I'm eating. So here, I'm going to ask you guys to do a few things here. So find at least 3 combinations of the 2 foods so that the amount of protein in your diet won't change. Okay, and then once you've done that, go ahead and look at 2 and 3. Okay. Okay, let's come together. I know not all of you got all the way through those, but I think we got enough to move on. So this vector 1, 2, this is the row vector of A. There's only one row vector. There's only one row. So the row space is just all linear combinations of that row, which is just all the multiples of that row. So all multiples are just going to be a line. A line through 0, 0 that goes in the direction of U. Okay, so that's the row space in this particular example. Pretty simple. But you guys came up with some values, some of you at least came up with some values for X and Y that would not change the protein content, okay? And we can translate that into an equation that is, well, let me do 1, 2 times xy equals 0, just 0. Okay, I don't have to write the brackets around the 0 if I don't want to, but it's just a real number. But the question is, symbolically, can you find an x and a y so that this is true? And we could rewrite that. We can think of this as a dot product of vectors if you want, but you get 1x plus 2y equals 0. So find some x's and some y's. So I want you guys to toss some out to me. What are some of the ones you thought of? Yes? 0, 0. Okay, great. Another one? 2 and a negative 1. Okay, another one? 1, negative 1/2. 6, negative 3. Others? Negative 4 and 2. Oops. You see a pattern going on here? What is it about all of those values? They all seem to fall on a line. Okay? All of the points on that line are the null space for this matrix. Okay? So those are all of those values. All those values are of the form a negative, 2x, and I could pick x, but they're all of the form 2 minus 1. Is that right? Yeah. Some multiple of 2 and a minus 1. Okay, so this creates a line. So I could pick 2 and a negative 1 as my null space. I could actually pick any of those values, as the basis for my null space. So let me pick, oops. Oh, come on. Okay, so there's my vector B. I'm going to pick that as the basis for my null space. What do you notice about the line? The line that all of those points that you picked fall on, and the row space. They're perpendicular. So line. Let me get this line. I'm going to put the line on that's the null space. There was an easier way to do this, but oh well. Okay, so that line down to the right, the null space. The one, yeah, down to the right, up to the right, is the row space. Okay, the null space is always perpendicular to the row space. Okay, it might be if the row space is a plane, then the null space will be a line that's perpendicular to that plane. if the row space is a line and you're in 3 dimensions, the null space will be a plane that's perpendicular to that line. So they're always perpendicular. And you can kind of see that here because this is a dot product. X and Y, you're taking a dot product with this vector. We can think about 1, 2, xy equals the 0 vector. Well, 0 vector is 0 point in this example. And what do we know about dot products that equal 0? They're orthogonal, right? Okay. So what if I change my value by, what if I eat 3 of the first food, a -1 of the second food? How much protein, how is it going to change the protein in my diet? Now that'd be 3 times 1 and a -1 times 2, right? So if I let x equal a -3, I'm sorry, 3, and y equal a -1, then what do I get out? I don't get out 0. I get out 1. 1, 2, 3 and a -1 equals 1. Okay? So that's the point F right there. So that's that point F. So, so the question is, can you find another point where where it would change my protein content by 1, that it would increase it by 1 gram of protein? Can you find another x and y coordinate? So a serving of food X and a serving of food Y, you could tell me that would change my protein content by 1. So talk to your neighbors, see if you can figure that out. So. Okay, has anyone come up with one? What did you get? A -1 and 1? Okay, so a -1 and 1. Oops. -1 and 1. Okay, someone come up with another one? Yes. 1, 0. Nice. Someone come up with another one? -3, 2. Okay, what do you notice about those? They all lie on a line, and that line is perpendicular to the row space. Now, why? What is going on here? Well, I can think of this vector F, I can think of this point as being some piece in the row space direction, and some piece in the null space direction. Right, if I do, let me just do, oh, no, let me do this. That didn't work. It still didn't work. Oh, I never wrote a line. I need F, I think. Yep. Okay, so all those seem to lie on the line. Well, I'm going to zoom in here. Intersect G and F. Oh, that's not what I wanted. I can't spell intersect. Okay, this point right here. Okay, K. So I can think about F. I can't think about it as the going over 3 and going down 2 in the what's called the standard basis. But, sorry, over 3 and down to -1. But I can also think about it as going in the row space direction up to K, and then in the null space direction down to F. Okay, it's a different way of thinking. So I can think about it not in how much X and how much Y, but how much of the row space and how much in the null space direction. But what's a change in the null space direction going to do for me? Let's use some algebra here. If I have any point, I can think of how much of the, oops, that's the wrong vector. This is the row space vector, the row space basis. And this is the null space basis, right? I can write any point on that plane as some combination of these things. They're linearly independent. There's 2 of them. I can span R2. But what happens when I multiply this by A? Well, that's going to equal A times C times 1, 2 plus A times D times 2 to the -1. And what's that? Well, this is just a constant, so I'm going to write that as CA 1, 2. This is DA 2 to the -1. So what do I end up with? Well, what's A times this? Well, what's A times any multiple of 2 to the -1? It's going to be 0. This is the basis for my null space. The way we got this was what vector can I multiply by A and get 0 out? Okay, so this will be 0. Anything over here will be 0. And all I'm left with is something about how much of the row space, how far along the row space I am, where in the row space I am. The only thing that matters then is, the only thing that matters, no matter where my point is, I can move that point around, but the only thing that matters is the projection of that point onto the row space, this K. If I know that, then I know what, I know where I'm going to get mapped to. I know where the output's going to be. Because anything on this line is going to go to the same point. Because as I move along the direction of the null space, it's not going to change my outcome. So, so one of the big takeaways of this is we can think of the input space. Anything in the input space, anything in this R2, but it might be R3, like in this case, oops, like in the first problem we were working with. Any point in that input space can be thought of as some dimension into the row space and some dimension into the null space. And the dimension of the null space won't matter one bit about what the answer will be after you multiply it by A. So the row space and then the null space give us a way of chopping up the input space. And the column space tells us is all about the output. The column space tells us where we could end up. So and anything in the row space gets mapped to the column space. But and in this case, the column space is only one number. We could put it on the x-axis if we wanted to. And so anything on that line on the row space gets mapped to some point on the x-axis. And anything that's anything on the null space just goes to 0. So the output space is really just 0 in the column space. Okay. Dang, I have a nice 3D example. We haven't talked about bases. Okay. Okay, so trying to get some intuitive idea about what a basis is and where you might see them. So visible colors require you need to give me 3 values, right, to tell me what color it is. And I can think about it in terms of red, green, and blue if I want. So you tell me how much red, how much green, how much blue, and I know exactly what color you're talking about. Okay, so this is a basis. It's a basis because if I were to add one more color, it wouldn't be a basis because I can already make any other color with just red, green, and blue. So it would be a linearly dependent set. But red, green, and blue, they are linearly independent, and they span the whole visible spectrum. So one of the nice things about a basis is there is exactly one way to talk about any point in the subspace with that basis. Okay, it's unique, and that's where the coordinates come in that you'll be reading about this next time. Is those 3 numbers in this case are you can think about it as coordinates in that space. So we already talked about what if I add pink? Well, then it's not going to be a basis. I'm going to have some redundant information. There's going to be infinitely many ways then I can talk about any number, and that's just cumbersome. Let's throw out pink so we can just talk about one way. A basis is not unique. So the hue, saturation, and luminescence, that is another way to talk about these colors. If I change my red, green, and blue values, this is just on paint. So if you change your red, green, and blue, you're going to see your hue, saturation, luminance. I can think about them either way. These are 2 different bases for the exact same space. Cyan, magenta, and yellow is another one. So there's 3 natural bases to talk about colors. And technically, color is not a subspace. It's not a linear transformation to go from one of these to another one. There's maximum values with visible spectrum. So it doesn't work to do the math. The math isn't linear to go from one to another, but the idea of a basis here fits really well. So just a foreshadowing of what you're going to be reading for next time. 3.5C is all about coordinates. Once I have a basis, I can talk about coordinates or the value of any point with respect to those coordinates. So the color, the red, green, blue, and the hue, saturation, luminescence, these are 3 different values for each of those, but they're actually talking about the exact same number. And sometimes we have coordinates in one system and we want to translate it to another system. That's what we'll be talking about next time. Okay, a basis is used to do JPEG compression. Why? Well, if you zoom in really far to an image like this, you basically get pixels, and each of those pixels, if it's black and white or grayscale, it's just some measure of how much gray it is. And JPEG, what it does is it takes any 8x8 grid, and it doesn't think about each of the individual pixel. It thinks about it as a big, thinks about it as a whole, and it builds up those 8x8, that 8x8 grid as a combination of these things. And you think, well, why is that better? Well, it turns out that, the ones down here in the lower right rarely come up in photos. They're pretty contrived. And so these rarely get used. So you can actually capture the exact same image with less information by using these things. And it turns out each one of these is actually orthogonal, so it contains unique information. So, and sound waves. So this is me saying hello, that top one saying hello. And one way to compress that is to take other sound waves and to build that sound wave as a combination of other sound waves. And it turns out you can do that. And you don't need infinitely many sound waves. You can do it with a fairly small number of sine waves or sine or cosine waves, and get super close. And that's the essence of linear combinations. I mean, the essence of kind of MPEG compression is they're taking some combination of sine waves and just regenerating the sound from that combination at the other end. So, but these are some examples of bases in the real world. Okay, questions? Oh, we need another hour on this. So, yeah. So I'll do my 3D example starting next time with when we do coordinates. I'll do my 3D example I have in GeoGebra for null space and row space, and hopefully that'll help. Okay, have a great day.